Hey there, all you cool cats and kittens. Welcome to week 10. And yes, I said week 10 and not week 9 in our Auto 50 Canvas class because of how everything got set up schedule-wise. We are technically in week 10. So we skipped from week 8 to week 10. So you did not see any mistakes on your canvas. We are now actually all caught up, so you can follow along with your syllabus and check out your tentative schedule to see what each week is going to bring. We're going to follow it pretty closely now that we're all caught up. So today we are going to talk about suspension and steering. I'm going to put these in two separate videos because they're kind of lengthy. Normally I would put them in two separate lectures. So this one is going to be suspension. So we'll go ahead and screen share with us. Y'all can look at the PowerPoint presentation that I gave you in your Canvas class. Module, any moment now. Loading. All right, suspension systems. So I'm not going to go through all of the objectives. There we go. It's caught up to me now. First and foremost, what does suspension do? I'm going to try to move this out of the way so I don't block anything. Okay, what does the suspension do? We know that it makes the ride feel nice. That's usually what most everybody thinks of when they think of suspension. If you are into performance type stuff, then you also know that it's a big deal when it comes to control of the vehicle and traction. So we're going to talk about a few of those things. So all of the components that are involved in that are going to be part of our suspension system. Let's talk about the components first. That way we understand what we're looking at. And then I'm going to talk about the systems and the different types of systems that you guys are going to see. First and foremost, when you think of suspension, the first thing that pops up into most people's heads are springs. So what do the springs do? We know they make this sort of bouncy motion. That motion's actually called oscillating, moving back and forth from its original form. But the springs are going to be responsible for absorbing road shock, which we'll get to later when we talk about shock absorbers. These springs are actually the shock absorbers. They are the ones that absorb the shock. We'll talk about what shocks do in a little bit here, but they have a very close relationship with springs. Our springs are responsible for absorbing road shock. They have two motions or actions when they are compressed. Let's say you go over a bump, jounce. That is going to push the wheel up into the wheel well, and your spring is going to shorten, right? If it's a coil spring. We'll talk about the different types of springs. That is where our tire moves upward. The other action is after jounce, we get a rebound, meaning that the spring fully extends, the wheel moves downward, and the oscillations of the spring are going to be that jounce, rebound, jounce, rebound. We want to limit that so we can have a more controlled ride. You don't want to be cruising around like everybody's in a lowrider, right? So let's talk about the different types of springs involved. So the different types of springs that we're looking at here are first ones are coil springs. And I talk about these ones first because these are the ones that you think of in your head when you think about automotive springs. When you hear the term spring, you think of a coil spring most of the time, right? Coil springs, as you know, are this sort of bar of wire or a steel bar material that is going to be heat treated. They come in different designs for different reasons. So first things first, let's talk about linear rate versus variable rate springs. Variable rate springs act differently than linear rate springs. So I'm going to get out of screen share here for a moment because I want to use the whiteboard to talk about this. Let me see if you guys can see. I'm just going to go ahead and say linear. When you hear the term linear, like on a graph, we're sort of looking at a straight line, and that's how linear springs act. A linear coil spring is going to be the same throughout its top and bottom, essentially. And this is, I know my drawings are so beautiful and perfect. But the thickness of our material, the diameter of our coil, the spacing between our coils are all things that are going to affect how that spring is going to act, which we know, some of us, some of you may not, some of you may know as spring rate, right? So an example would be if I compress, if we're talking spring rate, an example would be if I compress this spring 1 inch, how many pounds would it take to compress a spring for 1 inch? Let's say it takes 100 pounds to compress this spring 1 inch. A linear rate spring is going to be the same no matter how many. And so if I go, and I won't get into too much detail here, just some basic theory, but if I compress this spring 1 inch, I'm not measuring it, but we'll say 1 inch, that takes 100 pounds. If I want to compress it another inch, I'm going to have to add another 100 pounds, and then so on and so forth. But it's going to be essentially the same. If I add another 100 pounds, the spring will compress. If I added 300 pounds, it will compress the spring 3 inches. Now, a variable rate spring is going to be a little bit different. A variable rate spring, and I'm just going to draw one example here, will generally look different from top to bottom. And again, we're just talking one type of spring so far, but this just as an example, a variable rate spring will have a different rate depending on how much load you put on it. So the closeness of our coils tends, or the distance between our coils tends to be a way that people will change the spring rate from top to bottom on a variable rate. Sometimes they will change the diameter, smaller and larger, to change the spring rate on coils. Those are two really common ways to get a variable rate spring rate. But the most important thing to know about variable rate springs is that most of the time, the more weight you add, the harder or stiffer the spring rate is going to get. That way, let's say if you want, let's say for performance, right? You got your 98 Honda Civic, and actually this is me talking from my, let's see, if I lowered my Civic, I would have been about 16, 17. I was in high school when I lowered. I was pretty stoked about that. Not qualified to do it at all, but I did it. I put lowering springs from H&R on my 98 Honda Civic, and they were variable rate. They use the distance between the coils style design for that particular model. And as soon as I put them on, I was expecting a rough ride. I didn't know anything about springs at that time. I just knew that these are aftermarket performance springs, right? They were the lower level. I put them on and I was like, wow. Obviously I was happy with the ride height, because I dropped it about 1.5 or 2 inches, but it was just enough for me at the time. And I noticed that it rode exactly like stock. I was like, wow, these are crazy comfortable. I was expecting a much stiffer ride. And I thought, oh, well, that kind of sucks. I was hoping for a stiffer ride, at least for cornering, because at that time I was not concerned about comfort at all. I was 16, 17 years old. You're worried about performance. So as I start to get a little bit more aggressive with my driving, I noticed that these springs actually stiffen up in the corners. And that's when I learned about variable rate springs. Variable rate springs are going to sort of give you the best of both worlds. If I want a nice soft ride, I can still have that. But the more I compress my spring, the harder it is to push it down. So maybe it's going to take 200 pounds to compress it 1 inch, right? I'm just keeping this, and I'm not going to get too in depth in that. I'll leave that for a suspension class. It's a very fun topic, but that's what we're talking about when we get into a stiffer spring rate, variable rate. The more I compress the spring, the harder it gets to compress on a variable rate. So if I'm leaning into a corner, that's going to help me with my weight transfer and control and traction and all that fun stuff, right? So that is going to be your variable rate spring. Also, what if I have a truck and I work in a business where I need to be loading stuff, very heavy things in there, variable rate springs can help out a ton too if I've got weight or not in the back. So variable rate springs are very useful in a few applications. So let's go back here so I can get into this. So as I was mentioning, they can make it variable rate in many different ways. You can have different diameter coils, meaning if you're following my mouse here, the diameter of the entire coil here, I can have different coil spacing. I can even have different thickness of material, but not necessarily for variable rate. But let's just say the entire spring can be thicker or thinner to change the rate. And then, as I had already mentioned, they're usually get stiffer the further they are compressed to help with handling. Leaf springs are a different design. The plural would be leaves. They can be either mono or multi-leaf. Mono meaning what you might think, not the disease, but the number one. A monoleaf is the bottom one down here. It was very common in the Corvette design. It was actually, I believe, a sort of carbon composite material that Corvette used. So it's kind of crazy because leaf springs are known for being heavy duty, like in this upper picture right here. This one's a multi-leaf design, but we know leaves to be common in trucks, right? We see those a lot in trucks, not really in cars, not for a very long time anyways. And that is because they're better for heavier loads. They are a rougher ride for sure in coil spring designs. You can change the spring rate by adding or taking away these leaves, the thickness of the leaves as well. But not a lot of people know that the leaf design was used actually up until recently. I think actually just this year, Corvette changed the rear leaf design to I believe a coil design. I haven't looked at the new design, but I was at the LA Auto Show and they confirmed that they are no longer using the monoleaf. And I was like, what? So it is an old design. Nobody really uses it, but it doesn't mean that it wasn't good. I mean, these things held a G in the skid pad, no problem. Corvette, GM in general has a tendency to just really use the crap out of old technology very well by making it better and better and better and refining it. And you see that with the monoleaf, you see that with their overhead valve engines, but I won't talk too much about that. So let's stay on topic. Torsion springs or torsion bar springs, they don't look like springs at all. If you're not familiar with these, you'll look under a car, and it's actually funny because I used to teach high school, and even in some of the 50 classes, when we do the suspension inspection like we normally would in lab, people would look underneath the car on a torsion suspension and write NA for springs. Or no springs. First off, I would like to mention that anytime you guys go to look underneath a vehicle, unless it's a go-kart that is not high quality, any kind of car is gonna have springs. You're not gonna not see any spring at all. That's just, nobody does that. It wouldn't be good for anything. So if you don't see springs, you don't see a coil, you don't see leaves, and you're like, I don't see airbags, what the hell? It's probably a torsion bar, because the torsion bars look like other suspension components sometimes, and they blend in because it is simply a metal bar. Down here at the bottom is what it looks like. If you're looking at the top picture, you can see this one's labeled torsion bar. So here's what I want to get out, or here's what I want you to understand, because the way they work is a little bit funky. It's kind of cool. So first things first, what is this? This is not just your average metal bar. It is going to be a specific type of steel that is meant for twisting and turning. That's why they're called torsion. So if you remember back when we talked about torque, what is torque? It's a turning or twisting force. Torsion is a related term, and it is referring to a turning or twisting motion. So torsion bars are meant to turn and twist. Well, how do you turn and twist a metal bar? Here's how. So we're looking in the white here in the picture at a metal frame. And here we've got a cross member. Just because, okay, so let me explain. These may be on a unibody or full frame. Honda used these for a while on the CRX. There's lots of manufacturers, lots of trucks that use them. Chevy on the Tahoes, Nissan on their trucks, on the smaller trucks. So they're used all around. Here's how they do it. So they're gonna have some sort of cross member back here that is attached to the frame or unibody, but the frame nonetheless. Over here, and this is how they work in the front, not the rear, but the same principle. Here we've got something called a control arm. I know we haven't talked about this yet, but as the tire moves up and down, this control arm is going to move up and down and pivot on the frame. Well, since my control arm is moving up and down, let's say it's fixed to the frame here through a bushing, and it pivots like this as the wheel moves up and down. Well, what they did here is they took the torsion bar and they attached it like a puzzle piece. If you remember when you were a kid, putting the square in the square hole, it fits like a puzzle piece, and it's usually like a hex shape. So we've got a torsion bar that is put in like a puzzle piece into our control arm, so it can't spin. It turns with the control arm. So as the control arm moves up, my torsion spins at this end, right? So if I've got a bar here, as this moves up and down, that's gonna spin. I'm like using my arm as a piece here, but hopefully you get the point across. Back here, our frame does not move. It is a frame. It's sturdy, it's stationary. When I say stationary, obviously the vehicle may be moving, but the frame's not really doing anything. So one end is fixed to the frame, doesn't move at all, while the other end is attached to the control arm. That's the part that moves. Now, like any other spring material, it has a resting shape. And when I bend it out of my resting shape or I twist my torsion bar, it's going to want to return back. Just like my coil spring. If I compress my coil spring, it wants to return back. That's how we get that springy motion, right? That's how our torsion bar does it. There are different types of torsion bars. Volkswagen used an older design that had steel bars that went horizontally from the right to left in the front. It worked a little bit differently. I won't cover that in this class because this is just a principles class. And anything remotely modern you're going to see is going to be this design. I will say, yeah, no, nobody uses the front ones, not for a very, very, very long time. And I won't get into F1, but F1 also uses torsion bars in their push rod design, which is really cool. So what's really cool about torsion bars, if you look here, I don't have to have room for coil springs. So especially stuff, a lot of trucks use it because four-wheel drive. So I can have room for axles here because the space isn't being used anyways. So the torsion bars left room for other things, say when I didn't have room for a coil spring or an airbag or something else. Another cool thing about these, so coil springs, they're fixed unless you have coilovers, and I won't get too into that, but some coilovers, I'll talk about what that is if you're not familiar, so don't freak out. But if you know what those are, some coilovers are adjustable. What's really nice is pretty much most all of your torsion bars are going to be adjustable with your ride height. Now, with your ride height also changes your spring rate. So this is going to be the back side of our torsion bar. You can see going across here is our cross member. So this is attached to our frame. This would be going up front. So that would be the front of your car where it attaches to the control arm. If you look here, our torsion bar is fixed to this sort of lever piece. It's a key, essentially. So it fits in here kind of like a key, but I can actually twist the torsion bar in a fixed position by changing that lever point and tightening or loosening a bolt. Simply that will allow your vehicle to change ride height and spring rate. So you want to be careful with that. It's kind of nice because from the factory you have adjustable ride height, but you also want to make sure or take care not to adjust it extreme in either all the way up or all the way down, because you're gonna lose either travel, or it's gonna be a very, very, very stiff spring. And also, if you're doing this, obviously measure from right to left and make sure that you're making the same measurement on both sides. Air springs. Air springs are quite popular in the aftermarket world. You do see them factory in the snazzier vehicles. Jeep utilizes them, Lincoln, Cadillac, lots of really higher end vehicles may use this. Some use it for comfort, others for the adjustability of ride height. Another thing, most springs, if you're adjusting ride height, you are also adjusting your spring rate or changing your spring rate. And airbags are very much the same. So airbags do have different spring rates. They're actually really hard to calculate because it changes as you fill and deflate the bag, but they also change on the thickness of your bag material. The diameter of the bag will change the spring rate. The PSI inside the bag will change the spring rate. So lots of things that that really go into this if you're using aftermarket stuff. But a lot of times, especially four-wheel drive, like I said, a Jeep utilizes air springs for adjustability as well as spring rate. So if I go into a particular rock crawler mode or whatever mode I want to go into, it can adjust my ride height and spring rate to compensate for that type of driving. And that's really nice. Downfalls of air springs. So first things first, if it's a factory air spring design that uses sensors to accommodate for ride height. So meaning if it sees a change in ride height, it will deflate or inflate a bag to help rectify that. Well, if you put this vehicle on a lift or a jack, it doesn't know that you're servicing it. It just sees a change in ride height. And even sometimes with the key off, it will inflate the bag to accommodate for this change. And it may not have a limit. Lots of vehicles should have some sort of regulator turning off the feed to the bags. But if it doesn't, it will inflate to the point where the bag will explode. Like a balloon, and now you have to replace this possibly $1,000 for one assembly to replace this $1,000 assembly on your dollar, right? Because as a technician, you don't get paid for those mistakes. The customer is being like, "What the hell? I took this in for an oil change, and you popped one of my bags, or now I have to replace this." So you don't. You end up being responsible for this. So always, if you're working on something and lifting it up and it may have air ride suspension, it's not a bad idea to either disconnect the battery. If that's a complication, then at least pull the fuse for the air ride setup for either the computer for it, or what you could do is also pull a fuse for a compressor, disconnect the system, disconnect the sensors, whatever you need to do to make sure that the system is not going to try to inflate that bag too much. So always disable before raising the vehicle, because most of the time they are computer controlled from factory. So bump stops and jounce bumpers. So bump stops, they do the same job as jounce bumpers, but they do it differently, and they're made of different types of material. So bump stops, first off, let's talk about what they do. Bump stops and jounce bumpers, since they have the same job, their job is to essentially prevent metal-to-metal contact with the frame and suspension components, or suspension on suspension components. That way you don't have damage to components, and you're also not going to get this really, gnarly clunk inside the vehicle. You don't want to beat your frame or control arms or whatever it is, depending on the design, that you don't want to make contact. When and why would this happen? If you go over a bump that was a lot bigger than you thought, or a dip that was a lot bigger than you thought, and you get extreme suspension travel for that vehicle, sometimes components can hit. And to prevent that, we have bump stops or jounce bumpers. So bump stops are usually, they look like this, can be located on the frame. Sometimes they're located on control arms. They can be located on different components. They're generally going to be made of rubber or urethane material. And if you look at this one up at the top, it's actually a variable rate. So as it gets compressed, you can see this is thinner up here while we get thicker down here. So that's going to change the rate of that bump stop. Jounce bumpers do the same thing, but they do it a little bit differently. Their locations are usually different. So down here you can see these are struts. I haven't talked about these yet, but these little rubber pieces here, and they're not really rubber, they're actually a foam type material I'll talk about in a moment. This would be a jounce bumper. A lot of times they're located on the strut. Sometimes they can be located elsewhere though. Sometimes they're on the frame, sometimes they're on a control arm as well, just like bump stops. These are usually made of some sort of closed cell urethane foam. And so our bump stop, the rubber has a sort of springy or spring rate to it itself, right? Well, these jounce bumpers actually have air pockets or utilize air pockets inside the material to act as a cushion, almost like an air spring, which is really cool. They're a little bit better in how they do it because it is you can almost think of it as like a softer spring rate, if that's how you're thinking about it, than the bump stops. And so you may not get a loud thud. So if I hit the bump stop on my suspension or frame, I may get a loud thud. It won't be a clunk, but it'll be a thud, and you're going to definitely feel it inside the vehicle. It's sort of rough. Jounce bumpers are a little bit softer, which is why they're a lot more commonly used these days. Shock absorbers do not absorb shock. Their job, and it's funny because that's the name, shock absorber. I didn't make the name. They call water pumps, and they don't pump water, they pump coolant, but don't hate the player, hate the game. Do not absorb shock. They don't. Their job is actually to dampen coil oscillation. And when I say coil, any spring, I actually need to change that on there because it shouldn't be coil. It should be dampen spring oscillations, whether that be torsion, whether that be air spring, whether that be leaf or coil spring. But remember back when I talked about springs and that oscillation, that springing action from its natural state, compressed, jounce, rebound, right? Oscillations going back and forth between that. Well, we don't want the spring to be continuously doing that because a spring can do that for a long time, especially if it's pushed really far. And if you had no shock absorbers, you would be driving your car and you'd go over a bump and it would just continue to keep bouncing, even though you went over that bump, quite a ways back. You're still going to get that sort of leftover oscillation, and it'll get softer and softer until it's done. And then you go over another bump and the same thing happens. That is why we need shock absorbers. So shock absorbers are going to help limit the amount of times we get that bouncy. These are really easy to test. So I don't want to get too into testing or anything like that because we don't really have the option to go look at stuff. But if you're at home and you know how to use jack and jack stands, because I know we didn't do that lab yet, what you can do is you can take a look underneath your vehicle. If you want to inspect your springs, things, you know what, I'm getting ahead of myself here. Sorry, squirrel. Shock absorbers, let's stick with shock absorbers. I'll go back and talk about how to inspect springs, but shock absorbers, or struts, really easy to test. Go and bounce the bumper front or rear, but one at a time. Bounce the bumper, really get your weight into it, bounce the car, get some momentum going, and then let off. And count the amount of times the vehicle bounces once you've let off. 1.5 times is what your shock absorbers or struts are allowed. If you go past that, it means that they are bad internally and need to be replaced. Also, if you're looking at shock absorbers, it's normal for them to sweat. So you'll see sort of this outline, but it's not really wet. But they aren't allowed to leak. So if you see actually wet fluid coming out of shock absorbers or struts, they need to be replaced. Now, just real briefly, this is a little bit more of a complicated topic. I figured I'd just cover it, but I'll leave a suspension class to talk about it more in detail. Gas-charged shocks. What are they? Why do they exist? Gas-charged shocks, their job is to simply prevent foaming of shock oil, or what might be called dissolve. So there are air pockets in shocks. If they sort of start to clump up in areas that we don't want, we can get a change in it's not a spring rate. So if my shock absorber, first off, let me back up here. I've got, how does the shock absorber work? Because I can't explain why air is bad if we don't know why the shock absorber is bad. Our shock absorber has a cylinder, which is like a tube, right? And we have a piston that is attached to a rod that is moving through fluid. This piston is moving through fluid, right? The top is going to be connected to part of the body. The other is going to be connected to the suspension. So as your suspension compresses and releases, kind of with the spring, right? Our shock absorber is going to be having this piston move through this fluid. Well, that is going to create a drag, right? A piston moving through fluid. That's the whole purpose. So we want to allow movement, but slow it down. And using this piston with little valves and holes inside is going to allow some fluid through. Because if it didn't allow any fluid through, we'd get what we call hydrolock or hydraulic, which is what any hydraulic system principle works off of. We don't want that. We want the piston to be able to move. So fluid can't be compressed. Can very tiny little bit, but for the most part, fluid can't really be compressed. And so the piston has to have little holes or valves inside of it to allow fluid to travel through so the piston can travel through, therefore slowing down our spring oscillations. Well, if I get air pockets in places I don't want, then those air pockets, air can compress, while fluid cannot. So the air pockets are actually going to make the shocks feel way more squishy than they should. And that can change from side to side. That can change with temperature. We don't want that. So what we do with gas charged shocks is we put a little chamber, and I'm just going to talk about one design. I'm not going to talk about all of them or reservoirs or anything like that, because reservoirs do the same thing. But I'm going to have some sort of chamber somewhere. Sometimes it's in the shock. Sometimes it's in a reservoir that is going to be separate from my fluid, and is going to be charged with a nitrogen gas or pressurized with a nitrogen gas. Now, we're going to have a free-floating piston that separates the fluid from the gas. As my shock absorber compresses, the car moves down into jounce. The piston moves down, creating a pressure down here. It is going to push the fluid down, and this free-floating piston is going to sort of press up against the gas charge. But as it releases, so we go into rebound, the piston is going to move this way. We're going to get a change in volume up here. This free-floating piston is allowed to move up, and this pressure is allowed to continue to squish that fluid, kind of like a syringe. And the reason for this is to keep this fluid pressurized. If we don't keep it pressurized, it allows for these formation of air pockets. And when we get rapid movement, we get cavitation, which is going to help build up air pockets as well. And so pressurizing this fluid pushes either the pockets into the point to where they're so small it doesn't become a problem, or it pushes the air out. So this seal will allow air out. It will not allow fluid. It should not allow fluid out. So that's the principle of gas charged shocks. Like I said, sometimes if you've seen shock absorbers with a reservoir, that's where the pressurized gas is going to be rather. And I don't want to go too far down that rabbit hole because we'll talk an hour about gas charged shocks. Adjustable shocks. So there's a couple things I want to talk about. On the right here, we've got a knob that will usually, so remember I talked about that piston moving through the fluid, it has little holes or valves. Sometimes on nicer shocks or struts, because they work the same way, I can turn that knob and I can change the size of those holes in the piston. If I make the holes bigger, it's going to make for easier movement of that piston. If I make those holes smaller, it's going to make it harder for that piston to move and stiffen those shocks up. So that's where the adjustability comes in. Sometimes it's through the top, through an Allen wrench, sometimes it's through a little knob, some are electronic adjustment. Another snazzier design that a lot of vehicle manufacturers are starting to use now is MR fluid. It is a magnetic type of fluid. I know this is not really like a great picture, it's just showing particles in the fluid. But the magnetic fluid is a variable viscosity depending on how much current I send through the fluid. So if I send a certain amount of fluid, or I'm sorry, a certain amount of current through the fluid, I may be able to thicken up that fluid because it's magnetic and it can change whenever it wants to if I send a current through it. So not whenever it wants to, whenever I tell it to. And if I change that current, I can thin up that fluid or make it even thicker. If I change the viscosity of the fluid, that piston is going to it's either going to make the piston easier to move through the fluid or harder to move through the fluid. Thinking of swimming through water rather than swimming through honey, right? So these are electronically controlled. Now, just because it's electronically controlled doesn't mean that it uses MR fluid. There are electronically controlled shock absorbers that it simply changes the holes through an actuator. So anyways, like I said, GM is using this. Lots of manufacturers are actually picking this up. Lexus, I want to say, use this on some of the models, but this is a pretty sweet design. McPherson struts do the same exact thing as a shock absorber. They have a piston, they've got, the design changes a little bit, but the same principle. We've got fluid, we've got piston, a rod, a tube, valves in the piston and all that fun stuff. Does the same thing. It does something extra though on the outside. So the design of a McPherson strut is beefier. It's a larger piece. So the shock absorber doesn't have to, it doesn't have to provide a structural support. It is simply providing the action of what a shock absorber does. A McPherson strut also needs to provide some sort of support, and here's why. The type of suspension design, which I'll talk about in a few slides here, it requires extra support up at the top. The reason for this is it has no upper control arm. I'm moving a little bit ahead in saying that. I'll talk about control arms here in a few slides. But it also, know right now that McPherson struts provide extra support, and I'll explain why in a few. Not always, but most of the time, your spring is also going to be located. So it's all one piece. Your spring and your shock / strut are all one piece, which is kind of nice because it makes it really easy to remove and replace. If my spring is separate from the shock's usually easy to replace, but the spring needs to be compressed and decompressed, and it can be sort of a pain. Now, removing the spring off of the strut is a whole nother procedure we'll get into in a suspension class. Here's some pictures of some shock absorbers here on the left. You can see the difference, and on the right, we've got struts. So that's a big difference. Again, they do the same job. They just, the struts do a little bit extra. Down here at the bottom, you can see on the right, these are actually two different, this is what we call an SLA, this is a McPherson strut. But here's our shock absorber in between our suspension components, and here's our strut up here. Again, I'll talk about that in a few. Control arms are a key piece in pretty much all suspension systems. There's always some lying around. Control arms, and I don't have this written here, but control arms control lateral movement in and out of your wheel assembly. So we don't want our wheel, brake assembly, all that. We don't want that moving in and out. So there's got to be some sort of component that's going to keep that from happening, and that is our control arm. There is generally always a lower control arm. Some vehicles, depending on the design, have upper control arms. You can see in this picture here, I've got an upper and I've got a lower. But pretty much everything has front and rear, going to have some sort of lower control arm if it's independent suspension. Control arms can have either 2 or 3 mounting points. So if it has 3 mounting points, it can also be called an A-arm. And that's because it's in the shape of an A, right? I've got 1, 2, 3 mounting points, or a wishbone, because wishbones have 3 mounting points. So there's always going to be a single mounting point over where our wheel assembly is, and then over at the frame, so we have 2 connections, or 2 sides. We've got one side where it attaches to our wheel assembly. I'll talk about the knuckle in a moment. And then the other side where it attaches to the frame of the vehicle. You can see down here in the bottom picture, this looks like a Honda. We've got attachment to the frame here, and we've got attachment to our wheel assembly over here. This one is a 2-point, so I've got 1 mounting point here, 1 mounting point here. But if we look at the upper picture, we've got 2 mounting points where it attaches to our frame. So both inside and outside mounting points need to be able to allow for a pivot. So we are going to have different types of connections on each side, and I'll explain that in a few. So you can see here, upper and lower control arms look different. Here's why. Let me go back to stop share, because I want to discuss this for a moment. Oops. So way back in the day, we used, I'm going to go ahead and draw a wheel assembly over here. And I'll draw another wheel assembly over here. So I would have, we'll just, sorry, make my mounting points here. I really screwed that up. Okay, let's take this back here. That's where editing would come in. So we have to have something for our wheel to spin on, right? So back in the day, we had control arms that were equal length. The problem with this is as my tire moves up and down, it stays in the same position. We don't get a change in alignment, like meaning camber. You guys know camber, right? Where the tires move in and out. Not yet, because you have probably watched the steering lecture. But camber is going to be that inward or outward tilt of our tire and wheel assemblies. You'd think, well, that's perfect, right? We don't want any alignment changes as my wheel goes through the arc. The problem is, or the suspension, the problem is as you're going through a turn, you get weight change. And if I get weight change, I'm also going to have a shift of my tire, and the tire will actually lean on one side. We don't want that. We want a nice flat contact patch. We want as much of the tire touching as possible, especially in a turn, because the more traction, the more control we have. What we did with our control arms and anything, when I say remotely modern, even non-modern stuff, we've been changing the size of our control arms for a long time. So a big advantage of a new design, which we call SLA, we have short arms and we had long arms. This actually helped the camber of this tire change and go more negative as the suspension gets compressed. Well, that's a good thing, because as the vehicle leans over to that side, so let's say I'm making a left turn, my weight's going to transfer to that side. If I go negative, as that weight transfers, it's actually going to sit the tire perfectly straight up, allowing our contact patch to be optimal. So we want that camber gain. And I don't get that through equal length arms. I get that through unequal length arms. So if we go back to our screen share, you can see, come on, share. You can see my upper control arm is always, and you may want to make note, your upper control arm is always going to be shorter than your lower control arm. So we'll talk about that design. It's short, long arm in a moment here. What if my control arm only has 2 mounting points? So let's go back here. Let's look at these control arms. We've got 2 mounting points on the frame, 1 at the wheel. This is our A-arm. And the reason why you would want that is because it creates a triangle shape. So it allows not only in and out control, but it also leaves some front and back control, which is nice. Triangles are a very strong shape. If we go to a single control arm, this is a control arm that has 2 mounting points, or let's even go back to this picture here. I've got 1 mounting point here and 1 mounting point here. The problem is that controls in and out movement, but not frontward and rearward, and it's a single bar, not a triangle. So how do we strengthen that up? We add something called a strut rod. So Honda used this design or these components for a long time. Lots of vehicle manufacturers did. Ford did on many models. So of their cars. So it is used on the lower control arm when we only have a single mounting point on the frame. So what we do is we throw in a rod that attaches to the frame and the control arm, essentially turning it into an A-arm design. So, but there are extra bushings that you may want to think about. So we call this a strut rod when it goes from the control arm to the front of the vehicle on a frame. If it's, and this is sort of a general thing that I've heard, I don't really see it in any books where it lays it out for you, but sometimes if they're used from the control arm going to the rear of the vehicle, and when I say rear, just going that direction, to a frame or cross member, it does the same thing, but they may be called radius rods. Or if it does, you see this component in the rear, sometimes they call them radius rods. So it just helps keep the suspension rigid. Okay, now what ties everything together? Lots of times it's our steering knuckle. So we've got a knuckle that they can look a little bit different. This is an older sort of SLA design. But this is essentially a pivot point for steering wheels. That's why they call it a steering knuckle. So if my tires move from right to left, I need that pivot action of my tires. Well, how do I allow that? And this knuckle, through something called ball joints, I'll talk about in the next slide, it allows that sweeping pivot action of our steering knuckle. The steering knuckle is going to hold your brake assembly on, and I don't have this written down here, so you may want to write that down. It's going to connect, it's going to have your brake assembly attached to it, and it's going to have your wheel assembly attached to it as well. So that's something to think about. There are different designs. So if we look at this here, I want to bring this up because I feel like it took me way too long in industry to realize what pieces were what, and I felt silly as a technician not knowing proper terminology. So I just want to give you guys a head start on that. Up here, we have a steering knuckle. Down here, we have a steering knuckle. But if you look at these two designs, they are a little bit different. Up here, I've got lug studs and a flat hub. Down here, I have no hub assembly, but I've got this piece that sort of sticks out, that like rod that sticks out there. Here is the difference between top picture A and bottom picture B. Top picture A has the wheel hub. When I say wheel hub, I'm also referring to the wheel bearing assembly inside of it. So it actually uses a different type of bearing. And this piece can actually spin on the knuckle. My brakes and my tire and wheel assembly are going to attach to that, and I use my lug nuts and everything's all dandy. Down here, I have to have a special type of brake assembly that has the wheel bearing inside of that. It's an integral design that we'll get into. We'll talk about it when we get into brakes. Those are fixed rotors, while the top up here would use floating rotors. But down here, and this is the thing I really want to pay attention to, or want you to pay attention to, this is called a knuckle. Down here, this is a knuckle as well, but this piece that hangs off, that's called a spindle. So if it uses taper roller wheel bearings, it's going to have a spindle. If it does not, it is going to have no spindle. So these types of hub assemblies have no spindle. This one has a spindle but no hub. So just something to think about when you come across this, and people talk about terminology, and a lot of times to lower vehicles, you can buy knuckles where the spindle is located higher or lower to lift or lower the vehicle. you can't do that with these types of hubs. Or these types of knuckles. You'd have to lower the vehicle in another way. So anyways, neither here nor there. This is just something from my experience that I thought was really useful knowledge. And I felt like I learned a little too late, in my opinion. But a couple of things to know about your steering knuckle. Notice on both of these, I've got a rod that attaches to the front of that knuckle on both of them. All of your vehicles on the front are going to have that. These are something called a tie rod. I'll talk about in the next presentation. That is for steering. So this rod is going to push and pull the knuckle to change the direction of the vehicle. Nifty, right? Up at the top of our knuckle and the bottom of our knuckle, again, we need to allow for that pivot action. So this is where it connects to our control arms, usually through a ball joint. On a McPherson design, I'll talk about that. I will talk about it, I promise. Up here, we've got a strut instead of a ball joint. I'll talk about that. And then here you can see on the right on both of them, we've got some sort of bracket. That is going to be for your brake calipers. So that, in a nutshell, is your knuckle. Now, those ball joints where it connects the knuckle to your control arm, that is a ball and socket joints, kind of just like your shoulder, right? Or your hip even, it's a ball and socket joint. So I've got a socket down here. You can see it has a negative space and a ball that is allowed to rotate and or swivel and sort of move around angular wise in here. And there's going to be a layer of grease and a grease boot or dust boot that's going to protect all of that. Some of those ball joints are going to have what we call a grease fitting or a grease zerk on it. And grease zerks allow you to pump new grease into the ball joint to service it or maintain it. Not really service, sorry, that's the wrong term, but to maintain it. What you may find is that there's no grease zerk. Some ball joints don't have that option. Sometimes they're just like, well, when the grease is bad, the ball joint goes and you got to replace it. So not all ball joints are serviceable. Some are. Here's some pictures. Here is that tie rod assembly I was telling you. They use the same ball and socket joint. Down here is an A arm, a control arm, right? At the knuckle, we've got the ball joint here. And on the frame, we've got these two connections that are actually going to connect through what we call a bushing. So bushings, and here's an example, right? Let's say I've got a control arm that goes to my frame. Well, there's going to need to be some sort of give or movement, because if not, if it's simply a metal on metal pivot, you're going to feel so much from the road, and it's going to be very uncomfortable. So we have these rubber pieces in between our metal components, just like we have sort of joints and little like sacks of fluid in between our joints. So we have sort of a cushion. That's what your bushings are. And when those bushings wear out, they crack, they separate, they dry out. We get a clunking of metal material, and it's kind of like bone on bone, and you feel the clunk inside the car, and you get a sort of clunk sound. So we see these a lot in any type of pivot on the frame. On upper control arms, lower control arms, shock absorbers have bushings. Lots of components have bushings to help absorb that road shock. When you want to inspect things, just look at them. If you start to see them look like this, separating or chunks missing, they need to be replaced. A lot of times when you get complaints of clunks over a bump, that is because that is because your bushings are starting to go bad, and you may want to sort of take a look at it visually. Stabilizer bars, also known as sway bars, are going to be, if you look in the picture here, we've got this tan bar. That tan bar attaches to, your sway bar can either attach to the knuckle. Performance-wise, that's can be preferred on some higher model sports cars, or the sway bar can attach to the control arms. What the sway bar does, it sort of has like this goalpost sort of shape to it, right? And each side is attached to a control arm or the knuckle, And its job is to almost act like a torsion bar, but it's using that springy action to load an opposite side. Here's what it does. It prevents body roll during cornering. So when I'm making a corner, that weight transfer wants to create what we call body roll, meaning the body feels like it wants to go toward the outside. You feel this a lot in really big, old, heavy cars like Lincolns and Cadillacs. They feel like a boat, right? That is body roll. In a performance application, you don't want that body roll. Maybe you want a little bit of body roll, but you don't really want body roll because it's going to take away from my traction and control. So what we'll do with the sway bar is, as one side is leaning, it will transfer a spring motion to the other side and push it down, leveling the vehicle. So what we really want is, through a turn, we want the vehicle to be nice and level. And that's what our sway bar does. It's transferring load to the opposite spring, whichever is needed. So it's a really cool piece that most all vehicles are going to have them, anything remotely modern again. And when I say, I mean, we're even going to the 70s. They're going to have sway bars or stabilizer bars. Now, when you start to get into nicer models of cars, maybe like the higher end submodels, a lot of times they'll put in rear sway bars. Here's something to think about. Lots of people want to be gung-ho on their performance. So I'm going to get stiff springs and I'm going to get a stiff sway bar. You don't want to do that. So two big things that are going to control the amount of body roll you have is your springs and your stabilizer bar. Well, if I stiffen the crap out of both of those, I'm going to lose pretty much all my body roll, and there's a problem with that. Some of that body roll allows me to sort of dig into a corner and allow me to get traction. Little bits of body roll. If I completely lose my body roll, then I don't get that, and I may lose control, and I am not going to be as fast, or I'm going to crash. So you don't want to do that. Here's what you want to do. You either want to get a stiff spring and a softer stabilizer bar. Don't eliminate it. We still want it there, just softer. Maybe you leave it stock. If you want to go a little bit harder because you're getting too much body roll, then you can do that. But go incrementally. If you go just balls to the wall, then you are on both of them, then you're not going to have the desired effect. So stiff spring, softer sway bar, or softer spring, stiff sway bar, but don't go too stiff on either, on both of them together. So here's a better picture. Our sway bar is held in by two clamps and bushings that go onto the frame. On the end of each sway bar side, so you can see on the right and the left, we have something called a sway bar end link. That end link is going to have either bushings or joints that can be serviced or can wear out. So what can happen is, if these end links, I've seen them get so bad to where the ball and socket joint or whatever joint is there just completely came apart. Actually, my brother had a 97 Integra and said, man, this thing doesn't handle very well. And from him saying that, like, he doesn't take turns very aggressively at all. So I knew something was wrong. And when I drove it, I heard a clunk every turn, and I got so much body roll. I instantly knew this is a sway bar problem. Sure enough, when I lifted up the vehicle, the sway bar end link was completely broken off. Quick fix, and it stiffened it right back up in the corners. So this actually does a really big job. You'll definitely notice it if the bushings or the joints are bad. We can get clunking too from our sway bar bushings. So these are sway bar bushings. If you're looking at my mouse here on the frame, these are sway bar end links. The end links may have bushings or may not. Like this design doesn't use bushings. Instead, it uses a joint type of design. So anyways, just some points to talk about. Now that we know all of the components, there's something that is really important to talk about: sprung and unsprung weight. So hopefully you read the chapter. The concept isn't too crazy. So sprung weight is any component that is going to be supported by my springs, my body, my engine. I'm sorry, not my body, my engine, all of the passenger compartment. So yeah, I suppose our body, right? All of those things. Unsprung weight, some suspension components are sort of partially sprung or unsprung. Some are fully sprung, some are partially sprung, depending on where they're located with the spring. So components that are not supported by the vehicle's spring are things like your tires, your wheels, your brakes, sometimes axles. And here's the problem with that. You don't want a lot of unsprung weight because the springs are helping soften. A, it's helping soften up our ride, but B, it's also helping us control our vehicle in corners and such, right? So if we look at this, it's a kind of a silly picture down here, but I felt like it was a good way to sort of get the point across. I've got sprung weight up here, and down here I've got my wheels and whatever their frame is or whatnot that is attached. Over here I've got all of this down here, and only he is the sprung weight. All of this weight going up and down over bumps, that force of all of that weight moving up and down, that's called reaction force. So if you look at this top picture here, and this is why people want light wheels and tires, it's not just because the overall weight of the vehicle is less, but it changes your unsprung weight, which will help out immensely when we're talking about performance. So if you look here at my 30-pound tire and wheel assembly, if I hit a 2G bump, I'm going to get 60 pounds of force. If I increase that to 50 pounds, a heavier tire, maybe it's a steel wheel and a heavier tire, I change that immensely. Now I've got 100 pounds of force coming back into my passenger compartment, as to where with the lighter wheel assembly, I had 60 pounds coming into my passenger compartment. So it is definitely going to affect your ride. It's definitely going to affect your handling, because now I've got all this weight that I'm not really controlling with my suspension. And so it wants to fly wherever it wants to fly. And the heavier it is, the more it wants to fly in that direction. So unsprung weight is something we don't want a lot of. And in fact, if we can get the less amount or the least amount possible, that would be ideal. I've got a video to show you guys. I will tell you, I love Science Garage. I love you guys, but the last 2 minutes is sort of a sales pitch. So just keep that in mind when you're watching it. I put it in the YouTube links. Suspension designs, but it's a really good video. It's Science Garage Donut Media. You guys do a really awesome job, especially with your visuals. And so make sure you guys, you students, get a chance to watch that. It helps out. It gives you visuals that I can't. Suspension designs. Now that we know all the components, let's talk about how we put them together. So first things first, everything falls under an umbrella of either independent or non-independent. Independent suspension means each of these wheels can move alone and not affect the other. So if one wheel goes over a bump, the other is not affected, so on and so forth, right? So you can see here, I've got my frame in the middle. On this side, I've got a control arm. On this side, I've got a control arm. On a non-independent, also known as solid axle, it is simply the connection from one side to the other is solid. So if one side moves, everything tilts, and that's a problem, right? So if I hit a bump in the road, then the other tire is going to lean over and get my positive camber going, and I'm going to lose some traction there. And so that's sort of an issue if we're talking about cornering performance. Independent suspension is always going to be superior. In fact, in most cases, independent suspension is always going to be superior. It can get really, really expensive, especially when you start to get into performance or off-roading or rock crawling and stuff like that, which is why a lot of people will go solid axle, because you can get some decent amount of articulation out of it, but you are limited. Stock independent suspension, you may be limited, but that's why a lot of people will go aftermarket and get custom independent suspension to get better articulation. So neither here nor there. Moving on. Non-independent rear axle. So solid rear axles can either be one of two, dead or live. So a dead axle is simply essentially a piece of metal, almost like a frame material that goes from one hub to the other. This is, it's just simply, it's like a trailer. It's keeping your everything in line in the back, my suspension, my brakes, my hub assembly, all that good stuff. Everything's connected, but nothing besides that going on. A live axle is where I have a differential or a final drive. We talked about differentials the week before last. So an axle that actually produces power to the wheels is going to be a live axle. So this would be, say, a rear wheel drive vehicle, or maybe the front, obviously not this one, but I can have a front solid axle that is live on a 4-wheel drive. But most of the time on a front wheel drive, your rear axle is going to be a dead axle if it's solid in that design, and vice versa. Common independent suspension design. So those are non-independent or solid. That's pretty much as far as it goes. I don't want to get into too crazy stuff like 2 links, 4 links. I'll leave that for suspension class. Long arm. Okay, so let's talk about independent suspension. I have already kind of got into some of this stuff on accident, but we've got control arms, right? Same thing. We've got a knuckle. We've got a sway bar. Here's that tie rod I was talking about earlier. This is a short long arm, aka SLA design, also known as double wishbone. I already talked about, we use unequal length control arms. I already talked about why, to allow for camber changes while cornering. Something I want to talk about here, here's a real life picture with upper control arm, lower control arm. An advantage to SLA designs is the camber gain. But the problem is there are more components involved. So it's going to be more expensive to make, and it's also going to be more expensive to work on because we've got lots of extra components like bushings and joints and stuff that is not on other designs. So performance wise, it is a benefit, which is why you see in racing SLA being used regularly. But it is more expensive, which is why you don't see it on a lot of your common economical vehicles like Camrys and Civics and stuff like that. So here's the thing. This is really strange, and I don't know if I show up on there for you, but let me get that out of the way. There is a double wishbone, aka SLA design, that is modified. There's so many different names for some of the suspension designs. This is a term your book uses. I don't really like it because it's a little bit long, double wishbone modified strut. But it ties two designs sort of together. We still have an upper control arm, always a lower control arm. But what we did is we put a strut in there instead of a shock absorber. There's a couple of advantages to this. It makes it a little bit easier to work on. It also saves space. So let's say Honda used this type of design. They didn't use the design where my sway bar hooks up to the sway bar though. Their sway bar hooks up to the lower control arm. I won't get too crazy into it, but using a strut allows for room for a front axle on a front wheel drive car rather than using a spring and shock absorber. So this was used quite commonly. A full-fledged McPherson strut design. This is a true McPherson strut, has a lower control arm, as I said they all do, but on the top of the knuckle, instead of a ball joint, through 2 bolts and a mount here, we've got a McPherson strut, a true McPherson strut. So this is why we needed it to have structural support, because I have no upper control arm. The only thing that's keeping that knuckle assembly from moving in is going to be my strut. So my strut mounts to the knuckle at the bottom, and up at the top, it mounts to what we call a strut tower. It's sort of part of the frame on a unibody design. This is so commonly used. It's all over the place. Pretty much every front wheel drive car that is like any of your economical vehicles is going to be a McPherson strut. Hyundai, Kia, Toyota, Nissan, Honda. So many people use this. And the reason for this is it's cheap. It's cheaper to work on. It's cheaper to produce. There's less moving components. There's less bushing. So cheaper owner maintenance, right? Less things to go out. And it also allows room for drive axles. You can see here that axle going through here. So it makes things a little bit less complicated. There is such a thing as a modified McPherson. This is not very common. Ford liked to use this on the Mustang. It still has no upper control arm. It is a McPherson, but move me here. I've got a strut, but the strut looks a little bit different. It has no spring on it. Doesn't mean it's not a strut. A strut simply means that it is structural. So we've got that same structural support. The difference is the spring is not located on it. That's the only thing that's different. It is a little bit more heavy duty than the typical McPherson. We still have lots of, there's no space up front for any drive axle, so that sort of creates a problem, which is why you don't see it on front wheel drive cars, but the Mustang uses for a little while. Twin I-beam was really famous on the Ford Rangers. So this one's a little bit different. You can see on each side on the inside, I've got, well, let's look here. I've got two arms. They almost look like long control arms, and they kind of are. It's preventing that in and out movement, but they're really, really long. So on one side, I've got a connection to my frame, on the other side to where my wheel assembly is. And as the vehicle's wheel moves up, this whole arm pivots very much like a control arm, and it compresses the spring. Same on this side. This design allows for a lot more travel, which is why they used it. So it allows the wheel to swing through a wide radius because those arms are so long. And they call them I-beams because if I cut that arm in half and looked at it, it's skinny in the middle and has sort of two top halves, so it looks like an I. Now, again, these are not A-arms, so they need to use some sort of rod to control that front and back movement, so they do use radius rods. Adaptive suspension, I kind of already talked about MR fluid and adjustable shock absorbers and struts. It is simply that, but 100% computer controlled, so the driver doesn't have to do any adjustment. It's simply going to be a computer that is looking at ride height, looking at pitch, yaw, all these fun measurements, and says, all right, this is what we need to do, and this is how we're going to change the compression and rebound rates of our shock absorbers and all that good stuff. And a lot of times, if it has air suspension, it'll change your PSI on the fly really fast to change your ride height, all kinds of fun stuff. And also for spring rate. So I gave you guys a video in the YouTube links on Canvas. All right, that is going to be the end of suspension. I would like to just briefly discuss that you guys do have a test this week. We didn't have a test last week. I was taking it easy on you guys. Our test this week is going to include last week's homework and this week's homework. So wheels and tires, suspension, and steering. So make sure you guys do your homework. I will be doing a live Q&A this Wednesday at 6 o'clock, just like our class time would be. If you guys have any questions at all on the homework, or you guys had questions from Ms.A, anything like that, please, or just come to check in and say, hey, what's up? Long time no see. I will try to be up there for about an hour, depending on if anybody shows up. If not, I'll just shut it down. But if any of you guys have any questions about class, about the homework, about lecture, please write your questions down and I can discuss those on our Zoom meeting on Wednesday. I'm going to open up the quiz Wednesday morning. If you're just super confident, you're like, I don't have any questions, I'm going to take the quiz now, you can. If you want to wait, have your questions answered on Wednesday, and then take the quiz, you can do that too. So the quiz is going to be open from all day Wednesday, Thursday, and then all day Friday till Friday night at 11:59. So make sure you get your quiz done. If you have any questions, contact me. Hope this was enjoyable to you. So have a good one, guys. Thanks.